Do you hear me?
Uh, Good morning. So today we're talking about interpolation and extrapolation. A what's the difference between interpolation and fitting? If we have a given data for endpoints, let's suppose, and we say that given xi, we have the value or the evaluation of the function f at this xi for I goes from 1 to n for endpoints. So what's the difference between interpolation and fitting? What you've done in the lab, in physics lab, is fitting. So what's the difference? So what does that mean? Huh? There's no error. Exactly. So in interpolation, we suppose or assume that the values of the function given for us at these points are exact, are precise. There's no error in these values. So when we do the interpolation, we uh, uh, we uh, we we have to pass at these points of the data, and we are interested in evaluation or in the evaluation of the function at some point. Yes, in interpolation, it's this point is in the domain of these points. So that's what we want in interpolation. We want to estimate or to evaluate the function at some specific point given other points and given the exact values of the function at these points. In fitting, we are interested in the function itself, in the shape of the function or the functional form of the function, how it looks like, and we know somehow how it looks like, but there are parameters that are missing, and we sample the function with some error in endpoints, and we demand that our fitting is minimizing some metric or some quantifying uh, something that quantifies the total error of our fit. How is it far, or how far it is from the original function that we seek. So we are interested in the function itself in fitting. So if the first way or the most simple way to make this interpolation is by n minus 1 polynomial, and the Lagrange way is to say, how can I get a polynomial that is 0 at each xi except 1 xj, for example. So what is the polynomial Lj of x, the n minus 1 polynomial? It is of order n minus 1. That is 1 at x equal, it is Lj for xi is 1 if I equals j, and 0 if I differs from j. It's not j. So how can we build this polynomial? It's the multiplication over every I that is not j. I goes from 1 to n, but it's not j, of x minus xi over xj minus psi. Yes? So for every xi that is not j, one of these in the product will be 0, so it's 0. And if xi equals xj, let's say xi equals xj. No, yes, yes. So we have for all of them the value of 1, xj minus xi, xj minus xi, if the x is xj. Okay, and this is not 0 always, because the x's are different, all of them. Okay, and then if this is 1 for every for the xi and for the xj, and it is 0 for the other x's, so what is the polynomial that equals y1 for x1, it equals y2 for x2, it equals y3 for x3? What is? Exactly. So the polynomial is the sum of the yj's, j go from 1 to n, lj of x. Okay? So that is the Lagrange polynomial. Okay? You know it, but I think when we build it like this, it is more clear. And this way of construction has a problem. What is the problem? Not a problem, something which is a little bad. Yes, but I'm talking about uh, the aspect of algorithms. Why is it not so good? Yes, not difficult, but yeah, we can say it's difficult. Yes. So if I get n points or n sampling points of the function and I calculate this polynomial, okay, and now I want to improve the polynomial, I will add some another point. Yes. When I add another point, I have to recalculate everything. Okay. I have to recalculate the LJs and then do this. So if you have the polynomial itself and you add another point, you cannot somehow improve this immediately. You have to recalculate the polynomials. We'll talk about the but let's see an example first. So these are the points. 0 at 0 the function is 4, at 1 the function is 0, at 2 the function is -2, and again if we get we have this value 4 multiplied by, and we run over x minus xi over xj minus xi, except for the I, which is the first one. So we don't run over this 0. So we have x minus 1 and x minus 2 over the 0 minus 1 and the 0 minus 2. Okay, that's the first term. And the second term is 0. Why is the second term 0? Because the value of the function is 0. 0 multiplied by something 0. And then we don't go over this 2. So we have x minus 0 and x minus 1 over 2 minus 0, 2 minus 1, multiplied by the value of the function at that point. So that is the polynomial. And we know why we have n minus 1 polynomial. Yes, when you have 2 points, you can have a polynomial of order 1 that goes between them, which is a line, or a linear function. And if you have 3 points, you can put a quadratic function that goes exactly in these 3 points. So when we have n points, we have one polynomial, one n minus 1, one polynomial of order n minus 1 that goes at these points. Another disadvantage, yes, as you said, is that we don't have any estimation of the error. So a question of you, what do we mean by estimation of error in interpolating? What's the meaning of error? We don't have any data about the function, okay? Someone gave us the values of the function at some point, okay? So if someone gives you this value and this value, maybe the function is this. Maybe the function is this. And maybe much more, okay? So we cannot expect anything about the error. When, when we do fitting, yes, we expect something about the functional form of the function, and then we can say something about the error. But the concept of interpolation is that I don't know the function, but someone gave me a data of the function at some point, okay? So what's the meaning of estimation of the error? You can say no meaning, okay? So we're not estimating an error here. The treatment of the error is only by hope that if we go further by sampling the function, we do not improve our evaluation at the specific point that we want much, okay? So adding another point, adding more point doesn't improve my evaluation. That's the maximum that I can do. Again, maybe if there is a function and I give you values of the function, okay, not this value. You do an evaluation based on these 2 points, okay? And you say to me, for example, that's the value of the function. And I give you another, and you say me, okay, the value of the function is here. And I gave you another point, another point, another point, data, 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 and you are only in this region. So you say, after you got many points, you say to me, okay, you don't have to give me more data. You're not improving me so much. That's the maximum I can do by this way of interpolation. But again, maybe your error is this. Okay, it means only that that's the maximum I can do by your data. Okay. And because of this, you didn't have any proof in the in the class, because there is nothing to prove here. Okay. So how do we solve the problem of this complexity? We do it step by step by a tree. And when we do it step by step by a tree, if you have another point that you want to add to me, for example, x5, I will do some calculation, but I will use previous calculations, and I don't have to recalculate everything from the beginning. Okay, so that's a Neville algorithm. So if you use, let's say that I want to evaluate the value of the function at some point x that's not x1, x2, x3, x4. It is an x, about a specific x. You build the first polynomials from the first information. For example, at x1, you suppose that you have the information of x1 only. So your interpolation will be x1 is p1, which is y1. Okay, so that's the polynomial. It's a polynomial of order 0. Okay, and if you want to use only x2, you say the function is p2. which is y2. Okay. Now, if you want to use p1 and p2, you want to use the data of x1 and x2, you say, okay, from p1 and p2, I build p12. And if you want to use only x2 and x3, the data of x2 and x3, you say from p2 and from p3, and I build p23. The point x, it can be wherever it would be. Okay, so it can be less than x1, more than x1, but less than x4, and more than x4. Okay. If it's within the domain of x1 and x4, we call this interpolation. And if it is outside this domain, we call this extrapolation. And extrapolation is more dangerous than interpolation. We expect errors to be bigger there. And this way helps me to determine if I want more sampling errors from below or from above. So let's see. And how do we build any polynomial like this? That's the way we build it. So at the end, it will give me which polynomial? What is the polynomial at the end? What is p1, 2, 3, 4 will be? It will be this. It will be the Lagrange polynomial. But we build it step by step, so that if we add x4, x5, and we want to use it, so we add p5 and p4, 5, and then p3, 4, 5, and then p2, 3, 4, 5, and then p1, 2, 3, 4, 5. And the question is, for some point, let's say between x1 and x2, which is the best polynomial? Not the best. Can I stop to be given data or not? So, and an example of this formula is the P1 and P2. For example, what is P1 and P2? How I can build P1, 2? Or let's say, how can I build this from these two? Okay. The way is, I take x minus x3 multiplied by p12 plus, or let's say minus x minus x1 multiplied by this. So it's always the first and the last one. The first and the last one, if I want this. So how do I build this? From these two, I use the x1 and x3. Okay, that's the 1, 3. If I want to build this from these two, p2, 3, and p3, 4, I use the x2 and x4. So it is x minus x4 multiplied by p2, 3 minus x minus x2 multiplied by this over x2 minus x4. Okay, so this is a trivial example or simple example, and I gave you now a more complicated one. And again, if the point is, for example, between x1 and x2, and I'm asking, and I used x1, and I said the value at the point x, which is between x1 and x2, the value is y1. Okay, and after that, I added the data of x2 and improved my polynomial, and I said the value is p12 at that x. Okay, and after that, I used x3, more data, and said p123. That's the answer. So the question is, am I changing the value here significantly or not? For example, let's say that this value is 1, and when I used the x2, the value it's 1.01. And when I used x3, the value is 1.005. So that means that if I add more points, I would not be improved more than 0.05. So if that's the error I want to be as close as to, I can say no more data will help me more than this. That's the maximum I can get. And again, maybe the error is 1 million. Okay, but but you cannot give me. It seems that you cannot give me more data that changes the value that I will say significantly. Okay, and we talked now about adding more points from above, but there is a question also to add more points from below. So because of this, these are the differences that we talked about now. Right now, I talked about the differences, the C's. Yes, these are the C's. And the D's are from the differences from the polynomial that I get when I use more data from below. Okay. So this is P2. And if I use a data from below the x2, which is x1, I get the polynomial P12, and the difference that I get is the D. Okay, so when I add more points that are bigger than my point, or more sampling points that are bigger than my point, I ask about the differences, which are the C's, and if it's the opposite, I ask about the differences, which are the D's. And here is an example. And again, in interpolation, I'm asking about a specific point. If you are asking about another specific point, maybe I will prefer another data. Okay. For example, here maybe I will prefer the data only from x1 to x5, and you're not adding more information for my specific point, which is 0.15. But if you're asking me about, for example, 0.445, maybe I will say to you, I want more data from above. Okay. So this is a specific point, and the given values of the function are these. And now I'm using the Neville algorithm, and if I want to evaluate the function or to estimate the function at this point, that's what I get if I say I'm using only the data from x1, and that's what would I get if I use only the data from x2. But if I combine these two data, I get this. Okay, and if I add another point, the third point, I get this, I get this, I get this. And you see now, I'm not improving now. So it's, for example, I can say I can improve only at the third decimal point, and it's not important for me. That's it. It's enough. But here, as you see, if I wanted to evaluate the function at this point, only using this point, the value is is very far. And if I use x4 and x5, okay. And if I use also x3, okay. So I'm changing now. So it tells me that yes, you have to take more information from below, okay? Because you are changing. You see, this is a significant change. And now it's a change, but it's less. Okay, so this is in the second decimal digit, this change, and even it's an extrapolation. Why is it an extrapolation? This value is an extrapolation. Why is it an extrapolation? Yes, because this point is outside the domain. of x2 until x5. So although it's an extrapolation, it's somehow close to the answer that we would get from the interpolation. Okay, because the extrapolation also begins from a near point to the point we are asking about. Any questions? Yes. The d functions here, for example, this is a d function. Okay, so I wanted to use this value, and I'm asking now, what happens if I use a value from below? So that's the value from below. So that's my improvement. Okay, so the c goes like this, and the d goes like this. Okay. Okay, we talked about the errors. And now let's see an example. Suppose that we have a function that is x squared. That's the function. But we don't know that the function is x squared. Okay? Someone gave us 3 points of this function and asked us, what's your interpolation? So at these 3 points, there is only one quadratic function that passes through them. And our answer would be very, very correct, because we know that the answer is x squared. But suppose we don't know. Okay, so that's our interpolation. Now, he gives us another, he gave us at first 3 points, and now he gives us another 10 points, but all of them are here, all of them. And now he asks us, what's your interpolation function? Now our interpolation function would be a polynomial of order 12, because there are 13 points. So this polynomial would be this, if we calculate it by the by this equation, for example, or by our algorithm like this. Okay. So as you see, in this range, the range of the data, our interpolation is very good. But far from it, it is not good. Again, this point is also given. We used it in the interpolation. We used this point, and all these 11 points. Another way to say this, another way is, if we wanted to interpolate the function here, adding the data far from it ruined our interpolation. Okay? That's another way to say this. And it's a very good way, because maybe we are interested in this side of the function. So why is that? Again, when we make interpolation, we don't know the function. If we know that the function doesn't behave wildly, so we can choose the points in some good way, so that this would not happen. But if we don't know anything, and if we can only measure, for example, can only measure these points and this point and this one, that's the interpolating function that we can get. Of course, we can make this better, but I'm talking about Lagrange. So why is that? Because when we built this this polynomial, again, all the values here were supposed to be set to 0, and this is supposed to be set to 1. But when we used all these data, that's the answer. And in points here, this polynomial is built such that all the changes of the parabolic function, or the function of x squared, cancel out in these points. And you see this is an we have here a odd exponents and or odd powers and even powers. Yes. So the odd powers and the even powers somehow cancel out each other, and we get the value of the function in these points. But in the right side, the odd functions will change sign, and then terms will be added up, and then we get this oscillation. Okay. So maybe adding points in a far region cause oscillations in the region that we are interested in. Okay, so that's a point that you should know. And here in this example, that's because the function is symmetric. Maybe the function itself behaves like this. Maybe, I don't know, the real function. We don't know. So because of this, we have somehow to pick our sampling points in a good way. And here is another example of this function. And if we want a parabolic or to use only the 3 points, we get this parabola. And if we use more points, so again, you see the red line is not exactly on the black, or the opposite, the black is not exactly on the red line. And because we did not pick more points here, so the evaluation of the function here is not so good. Okay. And you have, I think the function, I don't remember that the function of function of the polynomial interpolation is not has changed. Yes, it is now not like the previous version in Python. Okay, I will check that. But anyway, we can use fitting also, and that's for you to know. And again, what's the fit? That's when I know that the function somehow have these values, but with some errors. So I ask, what's the best path between these points of the data, or of the given data, or measured data? And I know I make a minimization for some metric, which is some quantity that quantifies some global error of our interpolation or our fitting. And again, if some of the points has, for example, or some of the points have more errors than the others, I can take care of this in my metric, or in my this quantifying error or global error. And what you have done in the lab, in physics lab, is to say that the errors are somehow the same for all my samplings, and I want the line between these dots to be, and you know what's the shape of the line. For example, you know that it's quadratic, or you know that it is linear. And when you know that form, you say, for example, if you know that it's linear, you say it is ax plus b. And which a and which b I will choose? The answer is it's the a and b that gives you the minimal mean squared errors. So that's your metric. Okay. Okay. And I said mean, which means the average. You don't have the average here, but it's a constant, so it's the same. Okay. Any questions? Okay. So now we'll talk about another way of. It's a better way of interpolating. It's the spline interpolation. And here we'll talk about cubic spline interpolation. Renan talked about cubic also, or what? Yes, no? Okay. So now our way of interpolation is to say, okay, you gave me data. And again, in interpolation, I want the function to pass through these points. My way is between every 2 points, I connect some low order degree polynomial. Okay? Not n minus 1. I can use n minus 1. But for example, a cubic interpolation function, or a polynomial of order 4 or order 5 when I have 100 points, for example. But I will have many polynomials. Okay. So here I connect them by S1, and I connect them by S2. And this S1 is, for example, A1 x cubed plus B1 x squared plus C1 x plus D1. And this S2 is A2 x cubed plus B2 x squared plus C2 x plus D2. And this S will be Sn or Sn minus 1? Sn minus 1. Okay. And I impose some boundary conditions on these polynomials. So I will at the end of this process, I will have a smooth piecewise interpolating function. Okay. So in each segment, it is smooth, but when it changes from a segment to segment through a data point, some derivative would not be continuous. And this derivative is determined by the order of the interpolating spline that we choose. Okay, so for our purposes, we will choose cube or cubic spline because in physics we are interested in continuous second derivatives also. And in other purposes or in other applications, when you choose to, for example, when you choose fourth order spline, you have to know what you should choose for your conditions. So we'll talk about this in a second. And that's you will choose this based on something that you know about the problem. Okay. So, for example, if we're talking about some string which is uh, fixed in its ends, we know something about these ends. Okay. So we will choose for every si to be at xi and at xi plus 1 to be y, sorry, si, sorry, at xi to be yi, and we want si at xi plus 1 to be yi plus 1. Okay? So that's for this smooth piecewise interpolating functions to be a function to be passing through the points. That's what we what we impose. But these conditions are how many conditions are these? This is 2, and this is 2 multiplied by I goes from 1 to 10 minus 1. So these are 2 and minus 1 conditions. Okay. And if we add the condition of the first derivative to be continuous and the second derivative to be continuous, how much we get, how much constraints or conditions we get. So if we also say that si tag at xi plus 1 equals si plus 1 tag at xi plus 1, and we ask the same for the second derivative. How much conditions are there? So this is as we have n minus 1 polynomials, and we are connecting them by how many points? N minus 2. So this is 2 multiplied by n minus 2 conditions. Okay, but how many parameters do we have to fix at the end of the process? 4 multiplied by n minus 1. Okay, so every polynomial in the spline have 4 parameters, and we have to fix at the end of the process 4 multiplied by n minus 1. So how many equations are missing, or conditions, or constraints? 2. Okay. And these 2 are gotten from what we know about the problem. Okay. So for example, if we don't know anything, we can say at these endpoints, I ask the function to be I demand that S1 tag at this point would be 0, and the same is here, because I somehow assume that here because there is no data before, I expect from the function here in this neighborhood and also here to be maximum linear. Okay, so that's if I don't know anything, but maybe I know something. So if you know something, you can impose it. Okay, so you have 2 conditions to put in order to get the sufficient conditions to get your spline interpolation. Let's take for now a break. for 10 minutes and then go back. Any questions for now? Okay. Yeah, you see, we're close to finish. Okay, so why is the spline method or spline interpolation is better than the Lagrange interpolation? First of all, we expect that it's better. Expect. Why? Because there are more parameters that we seek. Okay. In the Lagrange, we expect. In the Lagrange method, we have n parameters that we find, but here we have 4 times n minus 1 parameters. So we hope that these added parameters improve something. Okay, so what do we improve in this method? Yeah, so it's less wild or violent, or we somehow ignore or avoid the oscillations, and especially there are oscillations near the points, the end points. They are called Runge. I think that's how we spell it. Runge oscillations. They are like the Gibbs in Fourier transform. And another thing, we somehow improve our error. Okay, what's the meaning of improving error? It's what we said. Okay, the maximum that we can get from something. Okay, so here we have an example of 3 points, and we want to make our interpolation. So if we have 3 points, so how many functions do we seek, or how many parameters do we seek? Huh? 8. So we have two functions. We have these 3. What are the values? -1, 3. -1, 3. And 0, -1, 0, -1, and 2, 3. Okay. 2, 3. So we have here some spline. So we have here S1 and S2. So the S1, we suppose it to be plus bx squared plus cx plus d. And this is E F G H. Okay, so here are 8 parameters, and we want that S1 at -1 equals 3, and we want S1 at 0 and also S2 at 0 to be -1, and we want S2 at 1, yes, a 2. So this is 2. Equals 3. Okay. So here are 4 conditions. And we start from which conditions? This, because they are easier. Okay. You can start from wherever you want. But if we want to solve this by hand, so this is easier to start with. S1 at 0 and S2 at 0. And because of that, we know, for example, that H equals D equals -1. Here we want -1. And we impose the other values. And then we impose our condition, our boundary conditions, which are the S tag here is continuous at 0. And this is also easy. Okay, because when you plug in 0 in a polynomial, you have only the last term to be not 0. Not exactly not 0. Maybe it's 0, but you have to check one term. So also the S tag at 0, we want it to be equal. So C equals G, and also B equals F. And then we have to use another two conditions, which are the conditions of S tag. For example, S tag at these points to be S tagain, the guy, S two tags to be 0. So we want the function to be at most linearly there, and that's the solution. Okay. So nothing complicated here to be done. Now, for you to know, if you know the values of the function, and somehow you know also the values of its derivative. For example, if you measure some particle and its location and its velocity or speed somehow. So you know the values and the derivatives. You can use some polynomials called Hermite polynomials. Have you heard about them? Yes, no. Okay, so you will. I don't know. You will, because these semesters, yes, but these semesters are 10 weeks, 10 weeks. You have to hear about them in quantum physics. I think you will. I don't know what they will teach this year, and what will they remove. Okay, so if we have this data, we can use some closed form that we already know, which uses these polynomials, the Hermite polynomials. Okay, so that's for you to know. Okay. In Python, the way that you make this interpolation, the spline interpolation, is by using enter 1D. Okay, so and you say for it the cubic, you give it the string or the vector of x and the vector of the values of the function, and then this would give you the interpolation. And let's talk now about the multidimensional interpolation. You didn't talk about it in the lecture, but it's easy. Okay, so how do we use how do we perform multidimensional interpolation? So let's suppose that there is a function of two two arguments, x and y. So it's a scalar function, f of x and y, and someone gave us some grid of this function, so some grid of sampling, yes, at some x's and y's. Okay. So we have two-dimensional grid of sampling, and we ask about some point in this range, which is not given for us, but it's in the range. It's interpolation, and we can also talk about extrapolation. But let's assume that it's interpolation, and we ask about evaluating the function at that point. So how do we do that? The answer is we make the problem one-dimensional in every dimension, and we use the result in the other dimension. Okay, so let's suppose that we have the values f1, f2, f3, f4, and we are asking about some xy in this range. Okay, so how do we do this? We say that we, for example, if we want to use only these points, okay, we say that we can evaluate or we can fix y here and ask what's the function that interpolates these two values. So it's a function f of x for a fixed yj. Okay, and then ask another question: what's the function f of x for a fixed yj plus 1? And that's another linear function. Okay, when we finish this, we have some f here, and we have some f there. And we interpolate now this function in the second dimension, which is the dimension of y. Okay? So in the first dimension, f of x, yj, so it's linear here. Okay? We're talking about Lagrange interpolation here. So f1, f2, how can I make a linear function? You know that. So it's f2 minus f1 divided by x2 minus x1 multiplied by x minus x1 plus f1. You can say f minus f1, maybe you are used to this way. F minus f1 is this. Okay, that's how you build this linear function. But we also know by Lagrange, we can build it in another way, what we said at the beginning. So that's the way that Lagrange told us, and they're equivalent, of course. Okay, so here we do some massage for the function, and we see that it's the Lagrange, or we can write it in the Lagrange form. Okay, so that's the linear function that interpolates the function only at this line. Okay, and we can build another function that interpolates at the second line. Okay, and now if I want the function that combines this and this, so it's somehow, let's say that this, think about this like something given like a constant. Okay, it's given that f of x at yj is a function of x. Okay, and this is another function of x, but think about them like constants. Okay, now we have f of yj equals something, and f of yj plus 1 equals another thing, and we want to interpolate. How do we interpolate? In the same way. Okay, so how do we do this? For example, for y, so let's say like this. I know that f of x1, x2, y1 is f1, and x1, y2. Let's make the same. Now I don't use I and I plus 1. I use 1 and 2. Okay. So x2, y1, f2, and I know that f of x3, y1 equals x1, y2, f4, and this is f3. So the interpolation function of these two for the same y1, for the fixed y1, what is? It is f of x at y1 minus f1 equals f2 minus f1 x2 minus x1 x minus x1. Okay. Okay. And from this, we get f of x, y, 2 minus, for example, f 4. It is f3 minus f4, x2 minus x1, x minus x1. Okay? It's the linear interpolation. Now, we have, for some y1, a value of the function. Let's call it like that. This is the value of the function, which is we call it f of x y1. And we have for f of x y2 another value of the function. Okay? So how do we interpolate these two in y now? We say that f of xy minus, for example, f of xy1 equals f of xy2 minus f of xy1 divided by y2 minus y1 multiplied by y minus y1. Okay? Hmm?
Don't have a square, we have formulas, right?
Ah, again, you're not in any dimension. You don't have. You mean something like this. Something like this. Okay. So something like that. Okay. Here's the answer. This way gives us at the end of the process which polynomial? Tell me. Which polynomial this way gives me? Which order? What do we have in this polynomial? We have the term of x multiplied by y, we have the term of x, we have the term of y, and we have a free term. That's it. We don't have x squared in this polynomial, for example. Okay? So I seek these parameters. If you are asking me a question like this, I write down this form of the function, and then I write down the value of the function at this point is like this, the value, and then solve these equations. If you have them in a grid like this, you can also make this what I said, but the complexity of the solution is big. So in the general given data, let's say, the complexity is big. But if the data is ordered like this, I can do this interpolation only at every axis and then combine them, and the complexity is much lower. Okay. Good question. Questions on this? And here we use T and U. If you understand the idea, that's enough for me. And all it's not, for example, I don't want you to use these T and U because this is only linear. I used only 2 points. We can use the grid itself, and then it would be another polynomial. Uh, so I want you to understand the idea itself. I make the interpolation in one axis and then use it as a value for the another axis. Okay, so here I show you how. Let's write a code that performs polynomial interpolation for the function absolute value of x in the domain -3 where n is 8 points, which are in equal intervals or segments. Perform the interpolation for 1,000 points at equal intervals and use the following functions. I think for fitting, that's the note I wanted to say to you. For fit, the numpy is now updated, and the function is called polynomial.fit. That's for fitting. So polynomial.fit. That's for you to know. So let's see. We can define the function. F is the absolute value of x. And if we want to make this from -3 to 3 and 8 points in equal intervals, you have this linspace order or command. It makes a vector of x like this. And here we can define the vector of the data or the array of the data. And then perform this polynomial fit. You see, we use polyfit and we use the poly1D. And the data itself, the colors are not good, are not correct. The data here is in orange. Not the data, the real function is in orange, and the dots are the data. And here we try to interpolate the function, so that's how we do it. Again, this poly1D makes the cubic spline. Okay. And here I show you how to implement the Neville algorithm. Yes. So you have to give it the vector itself, x, and the vector of the values, and the number, the number that we want to interpolate in, okay, or at, the point that we want to interpolate at. And you see, this is some loop, because that's how the algorithm works. But again, if you want for the algorithm to be able to get more data, so that's not the way that you implement it. Okay, it has to be more, and that's it for today. I think, yes. I don't know if this is good to you or not, but we have short recitations, I see. I don't know if I faster than Noam or why. So you prefer, I got some student told me that you don't have to make it bigger. So you want me to add questions to the recitations in order for this to be 2 hours? Because I see that we are in the third one, and also in the three of them, I finished before the 2 hours. I have to add more questions in the recitations. Yeah, because some students told me, no, you don't have to. Okay. So that's it for today. We'll see what we will make the next week. Do you know that if in the next week we should have an exercise or we shouldn't? You don't know. So okay. So I'll ask. Okay. So see you next week and some review for what we learned, or maybe I will see. I will ask Renan because we didn't learn much.